All right, now we're going to cover section 11.10 about what are called Taylor and Maclaurin series. And this will be the last section we cover from chapter 11. Okay, so just a brief reminder. In the previous section, 11.9, we were talking about examples of functions. For instance, 1 over 1 minus x, which could be written as a power series, summation of x to the n as n goes from 0 to infinity. So we say that this function has power series representation this. So what we want to do in this section, 11.10, is come up with a method for determining a power series representation for other functions that don't just arise from pre-existing power series that we already know. All right, so let's think of it this way. Suppose we have a function f of x, and let's assume it has some power series representation. And just to make things a little bit take up a little bit less space on my board here, let me assume that this power series representation is centered at 0. So I'll write it like this first, but then I'll write it in the expanded form. So we assume we have a function f of x, and it can be written as the power series summation of cn times x to the n, as n goes from 0 to infinity. So cn is just the sequence of coefficients. And so, again, for simplicity, I'm going to make this a power series centered at 0, so it's just x to the n. I could do the same thing with x minus a to the n if I wanted to use a different center instead of 0. Okay, so we assume we have this. Let me write it out as the first several terms, and let me try to make better use of my space here. So we're assuming f of x is c0 plus c1x plus c2x squared plus c3x cubed, and we'll do dot 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 after that. So we have this infinite polynomial representing f of x. What we want to do is figure out what these coefficients would have to be. So if I want to know what is c0, well, if I plugged in x equals 0, all these powers of x would be 0. So c0 has to be whatever the function value at 0 is. Right? So let me fill these in as I go. C0 would be f of 0. So now we have to figure out, okay, what is C1? How would we figure out C1? Well, there's not really a convenient x value I could plug in that would get rid of everything after C1, but leave C1 there. So I can't really, I've done all I can from this, from the original function. So here's the trick. Now I take the first derivative, f prime of x. Well, the derivative then would be f of 0 is a constant, so it'll disappear. Derivative of c1x would be c1, then plus 2c2x plus 3c3x squared, and so on. So there's f prime of x. Now if I wanted c1, I can plug 0 into this. So c1 has to equal f prime of 0. Right? So let's alter my coefficients now. C1 is f prime of 0. Now if I want to know C2, I do this trick again. Take the next derivative, f double prime. So f double prime of x would equal, well, now C1's constant, so it's going to disappear, 2C2 plus 3 times 2, let me leave it like that, it's 6, but 3 times 2 C3 x. The next one would be, from here to have 4 C4 x cubed. So I get 4 times 3 times C4 x squared. So now if I want C2, I would need to plug in x equals 0. All this stuff would disappear. I'd have 2C2 would have to equal f double prime of 0. But then C2 would be f double prime of 0 divided by 2. So let me fill that in here. C2 is this, f double prime of 0 over 2 x squared. And so we just keep on doing this. It's the same idea the whole way, it's just we're going to get more and more things that we have to divide by. So let's do one more. If I want C3, I'd take the next derivative, so that's f triple prime, the third derivative. 2C2 is constant, so it's going to disappear. We get 3 times 2 times C3 plus 4 times 3 times 2C4x plus some more stuff. Now if I plug in 0, I get 3 times 2 times C3 equals f triple prime of 0. Now I have to divide by 3 and 2, so I have to divide by 6. So C3 is f triple prime of 0 divided by 6, but let me write 3 times 2, and really I can put a times 1 there because we got a 1 when we I guess when we, well, it's a philosophical question. When do we get to pick up the times 1? I guess it's this last time. When I take the derivative of x, I'm taking a 1 down and then have no x's left over. Anyway, it doesn't matter. The point is, I want to point out the pattern. This is 3 factorial. 3 times 2 times 1. So C3, this is the last one I'll do explicitly. C3 is the third derivative of f evaluated at 0 divided by 3 factorial. 2 is also 2 factorial. 2 is the same thing as 2 factorial. 1 is 1 factorial. So a pattern is clearly emerging here. In general, let me erase all this stuff. If we keep this up, we get that under these assumptions that we already have a power series representation for f, then that power series representation will have coefficients according to this pattern. So the coefficient for x to the n would be the nth derivative of f. So you take the derivative n times, we plug in 0, and then divide by n factorial. Okay. So let me state this more formally now. That was just to illustrate where this next thing comes from. So here's the theorem. If f of x has a power series representation centered at A, so centered at the x value A, with a positive radius of convergence R let's just call it radius of convergence with positive r, then we can explicitly say what it is. F of x equals, here's the power series. Now it's centered at A. The example I did was centered at 0, but it's centered at A. It's the same idea, but we have x minus a to the n, and then the coefficient for that term is, I take the nth derivative of f, but now, in order to kill off the higher degree terms when I was doing my trick like in the previous example, instead of plugging in 0, I plug in x equals a, because that'll make the current terms that are still there, that'll make them go away if I plug in x equals a. So f, the nth derivative of f at a divided by n factorial. All right. So this is called the Taylor series for f centered at a. All right. So here, let me reiterate this. If I have a function, f of x, I can make up this series as long as the derivatives keep existing at a. As long as f has every single derivative at a. So it's infinitely differentiable at a. All of its derivatives exist at x equals a. If that happens, I can write this series. However, just because I write this series doesn't mean it's equal to the function. What this theorem is saying is, if we already know that f of x can be written as a power series, centered at a with positive radius of convergence, then the power series has to be the Taylor series centered at a. We don't have to worry about what it is. If it has a power series, it has to be this one. All right. So one other quick definition. The Taylor series centered at 0 Taylor series centered at 0 that's what we call a Maclaurin series. Of f. So that's what I did in that initial example. I was centering at 0, so the thing I came up with there is the Maclaurin series. Now, informally, Taylor is a much easier word to say than Maclaurin, so I will frequently refer to Taylor series, and frequently those Taylor series will be centered at 0, so technically they are more accurately called Maclaurin series. But they're basically the same thing. It's just a question of what x value we're centering it at. Okay, so let's do an example for a specific function. So let's do the Maclaurin series for e to the x power. So f of x equals e to the x. Okay, so let me write the general formula first, and then we'll do the work to figure it out for this specific example. The Maclaurin series looks like the nth derivative of f, since it's Maclaurin, it's centered at 0, so we're going to plug in 0 to that derivative, divide by n factorial, and then multiply that by x to the nth power. So what I'm trying to do then is figure out what is this coefficient in the case where f of x equals e to the x. Okay, So let's make a table. This one's pretty easy, but let's go ahead and make a table. So we want to have the nth derivative. Actually, let's make the first column n. And the second column will be the nth derivative of f. And then the third column will be the nth derivative with 0 plugged in. And then we'll just divide that by we'll take this column's value and divide by n factorial. And then this last column will be our coefficients. Okay, so that hopefully that'll be enough to figure out the pattern, and this one will be easy. So our n's start at 0. So 0, 1, 2, 3, 4. The 0th derivative of a function, that's just the original function. If I don't take the derivative at all, I'm just starting with my original function. So the 0th derivative of e to the x is e to the x. So I plug in 0 to that. E to the 0 is 1. And then 0 factorial is 1. That's defined to be 1. So 0 factorial equals 1. That's just a fact. So 1 divided by 1, that's my first coefficient. Then I've got n equals 1. That's the first derivative of e to the x. That's still e to the x. So you can see this is going to be a simple example. If I plug in 0 to e to the x, I get 1. Now I'm going to divide by 1 factorial, which is still 1. So I got 1 there. The next derivative, I just keep taking derivatives here. E to the x. I'm going to keep getting e to the x in this column because it's always its own derivative. Now I plug in 0 again and get 1 here. Now it's 1 divided by 2 factorial. Well, 2 factorial is 2, so that's 1 over 2. I mean, maybe I should show my work here. Okay, the next one, the next derivative is still e to the x. E to the 0 is still 1. So 1 over 3 factorial, that's 1/6. And lastly, that I have room for, the fourth derivative of e to the x is still e to the x. E to the 0 is still 1. Now I have 1 over 4 factorial. 4 factorial is 24. So 1/24. So these are my coefficients. Where can I write these? I guess I can. You've got them written. I can erase and do the next stuff without it. So, if I was going to write it out, I'd say this sum is 1 plus 1x plus 1/2 x squared plus 1/6 x cubed plus 1 over 24 x to the fourth. And it goes on forever. But I really want to know what is the sequence of coefficients. What is the formula for the sequence of coefficients? Well, these numbers, and here's where I shouldn't have erased, but these numbers, what they all were just, before I simplified, these were just factorial. 1 divided by a factorial. So this was 3 factorial. This was 4 factorial. So, what this is, what the series actually looks like is, my coefficients are just 1 divided by this exponent factorial. So 1 over n factorial. Okay, so the Maclaurin series for e to the x is this. It's x to the n divided by n factorial, and you add it up. So frequently it'll write it like this. X to the n divided by n factorial. So what we can do then, we have this power series now. I think I actually did this one the other lecture. If we have this power series, we can ask the question, what is this radius of convergence? So I'm pretty sure this was one of my examples in the 11.8 section when we're doing examples of finding intervals and radius of convergence for a power series. If not, it's a simple exercise. If you do the ratio test on this, you get the radius of convergence is infinite. So this converges for every value of x. But there's still the question. So we have the Maclaurin series for e to the x. We have there's still the outstanding question: does e to the x equal this? So what our theorem said was, if e to the x has a power series representation centered at 0, if it has a power series representation centered at 0, it would have to be this Maclaurin series. So that's still, we haven't answered it. It turns out that it is true. Okay, so yeah, it turns out that yes, e to the x equals this power series for all x. And that's because the radius of convergence is infinite. Okay, I think I was really dreading trying to explain the argument for why. How do we know when a power series equals its function? When a function equals its Taylor series, or when a function equals its Maclaurin series? So I don't think I'm going to try to explain it in this format. It'd be too difficult to follow and understand. There is an explanation in the chapter, so if you're really interested in that right now, you can read up about the Taylor inequality and how that relates. But for our purposes, I'll just I'll show you one or two more Maclaurin series or Taylor series, and we'll figure out the radius of convergence, and then we'll just state that for these examples they do actually equal the function. Okay, so let's do another one. Okay, so let's do cosine x. The Maclaurin series for f of x equals cosine x. Okay, so we'll do the same thing as before. I'll make a table, and then we'll figure out the coefficients and try to come up with a pattern for what the formula is for the coefficients. So in 0, 1, 2, 3, 4, how far should I go? We'll go with 4 for now. I've got room if I need to do more. Then we want the nth derivative. It's a Maclaurin series, so then we're going to plug in x equals 0 to that derivative. And then after that, we divide by n factorial, which gives us Cn. It gives our coefficient Cn. So it's this column divided by n factorial. Okay, so n equals 0. That's just our original function, cosine x. That's the 0th derivative. Okay, then cosine of 0 is 1 over 1 factorial, or 0 factorial, 1 over 0 factorial is 1. I'll keep track of what the unsimplified version is, because that's what we're going to use for the general pattern, I guess. When n is 1, the first derivative of cosine is minus sine x. If I plug in 0 to sine, I get 0. Sine of 0 is 0. So then 0 divided by anything is 0. Now the next derivative, the second derivative, that would be minus cosine x. And if I plug in 0 to cosine, I get 1, so this is minus 1. Then I divide by 2 factorial, so minus 1 over 2 factorial. That's negative 1/2. Now we keep going. The next derivative would be the derivative of negative cosine. That'll be positive sine x. Plug in 0 to that. Sine of 0 is 0, so my coefficient is 0. And then 4, the next derivative would be cosine x. Cosine of 0 is 1 again. I'll have 1 over 4 factorial, which is 1/24. But, I mean, this is, now it's going to repeat, right? A lot of it's going to repeat. We're back at cosine x, so the next derivative will be minus sine x. We get 0 and get 0 for our coefficient. Then after that, we get negative cosine x, which would give us negative 1. Then we divide by whatever the n factorial was for that row. But there's a clearly a pattern emerging. Every other coefficient is 0. The non-zero coefficients have an alternating sign. So we're going to have a negative 1 to an nth power or something similar to that in our coefficient. Okay, so let's write this somewhere. Guess I can try to do it here. So my power series is going to look like n. What n is the exponent on x. So if I just write out what I have so far, I have 1 x to the 0 minus 1 over 2 factorial x squared. I don't have an x to the first because I had a 0 coefficient. Then I have plus 1 over 4 factorial x to the 4th. And it's going to continue from there. But it's going to look like this. It's going to be an alternating sum of even powers of x. So let's figure out what that is, what it looks like. So my Maclaurin series would be, well, we have x to a power, but I don't want to put in anymore. If I put in, then that's going to give me odd powers of x as well. And I could make it work, but then my coefficient would be more complicated. I want to just kind of go with the non-zero terms in my sum. I don't want to have coefficients that are sometimes 0 here. So to make that work, I only want even powers of x. So let's make this x to the 2n. And so then what do I have as my coefficient? Well, let's do the easy part first. In the denominator, I've got this factorial. It's the factorial of whatever the exponent is. So 2 factorial. 4 factorial. 2n, that's 2n factorial. The factorial matches the exponent. Okay, then I've got this 1 on top of each of them, but with an alternating sign. So that means I'm going to have a negative 1 to a power. But now let's be careful. I have a minus for 2. So that's when n is 1. So I should have negative 1 to the n. Yes, when n is 0, I'd get negative 1 to the 0 is positive 1. That gives me this plus 1. When n is 1, I get x squared, and negative 1 to the 1 is minus, so I get a minus. When n is 2, I get x to the 4th, and negative 1 squared would be a plus. So you just want to make sure you use the correct exponent on the minus 1. When you know it's alternating, you know it's negative 1 to something, You want to make sure it's either n or n minus 1, depending on which terms are positive and which ones are negative. So you just want to make sure it agrees with what you want. All right, so this is my Maclaurin series for cosine x. Again, this doesn't tell us yet that they're equal to each other. So it turns out that cosine x does equal this power series. The proof of that involves this concept called Taylor's inequality, which you can read about. But instead, let's for practice see what the radius of convergence is. So what is the radius of convergence? Well, again, we got a factorial, so that tells us to use the ratio test. This is just like a problem now out of 11.8. So do the ratio test to determine what x needs to be to make this convergent. So we do the limit as n approaches infinity of the n plus 1 term, so negative 1 to the n plus 1, divided by, well, let's put the x to the power. So negative 1 to the n plus 1 times x to the power. Here's the trick. I'm plugging n plus 1 in place of n. So it's not 2n plus 1, it's 2n plus 2. Because if I replace n with n plus 1, that 2 gets distributed to both terms. 2n plus 2 times 1. Same thing here. 2n factorial, when n is replaced by n plus 1, that's 2n plus 2 quantity factorial. Okay, then that's our n plus first term now. Now we divide by the nth term, so that'll be 2n factorial divided by negative 1 to the n x to the 2n. Now technically, we're taking an absolute value, so it doesn't really matter about the negative ones. I'll leave them there since they're already there, but I could have just left them off. So if I do my cancellations, I have a negative 1 on top that's not on the bottom. So I have one more negative 1 than on the bottom. I've got 2 more x's than I have on the bottom. If I divide x to the 2n plus 2 divided by x to the 2n, I'm subtracting the exponents, so I have 2 left over. So x squared on top. Divided by, well, factorials. 2n plus 2 is bigger than 2n. It's 2 bigger, so this will have 2 extra factors that the top doesn't. So I'll have 2n plus 2 times 2n plus 1. All right, now cleaning this up a little bit. An absolute value will make that negative 1 go away. X squared is always positive, or always non-negative. So I've got x squared over 2n plus 2 times 2n plus 1. All right, and then remember, the limit is with respect to n. So n is growing to infinity. X is constant. X is not changing here. So this is a constant divided by something that's growing to infinity. So constant divided by infinity, that's 0. And in the ratio test, if our answer is less than 1, which 0 is, that tells us this is definitely convergent. It doesn't matter what x is, this series is convergent. So our radius, r, is infinity. We have convergent no matter what x is, so it's convergent for all values of x. All right. So we can do this for other similar kinds of functions. Excuse me. We can compute the Maclaurin or the Taylor series if we want to use a different center, which sometimes we may want to use a different center because, for example, if I was doing ln of x, if that was the function I was trying to do this for, ln of x is not defined for x equals 0, so I can't center its power series at 0. I'd have to center it at for example, 1, maybe. Would probably be the best place, or the easiest place. So in that case, if you have a Taylor series centered at 1, but you do the same process. You'd find the pattern for the coefficients, and then you get a power series. Then you want to figure out the radius, so you do the same stuff we were doing in 11.8. All right, so there's a table of functions in this chapter in the book that tells you some Taylor series and Maclaurin series for various functions and what their radius of convergence is and so on. I think with my remaining time on this lecture video, let me attempt to give you a graphical interpretation of these things. In class, this is where I would do this on a graphing calculator on the overhead, but I don't really think I have a good option for that here. But here's the idea. So let me use the cosine one I just did. So cosine has a graph that looks roughly like this. So that's y equals cosine x. What we are doing with these Taylor series, let's see what colors I got. Okay, so let me write this Taylor. Let me write the first few terms of the Taylor series for cosine x. So it was, well, the first term was 1. So if I were to graph that, here's 0 here. If I were to graph that, I'm not going to draw it because it's just a waste of marker. It'd be a horizontal line at y equals 1. So what that is it is the 0 degree polynomial approximation of this cosine curve centered at 0. And so what that would mean is it agrees with the curve exactly at x equals 0, and it does its best to approximate the rest of the curve with a 0 degree polynomial, a constant polynomial. And that would not be a very good approximation because this is not a line. The line would just be close to it, very, very near to x equals 0. So then I would want, what is the degree 1? What is the best degree 1 polynomial approximation of this curve? Well, for this one, it would still be a horizontal line because this curve is flat right near x equals 0. So this would also be my degree 1 polynomial approximation. And that's because in the cosine power series, it doesn't have a degree 1 term. It doesn't have an x to the first power term. So I don't get a better approximation by introducing an x. But what about parabolas or quadratic polynomial, degree 2 polynomial? Well, there my next term would have been minus 1/2 squared, 1/2 x squared. So this is the degree 2 Taylor polynomial for cosine x. And what that would be is a parabola that touches this cosine curve right here. It opens downward like this. I don't know how good it is, but it's a parabola, so it's going to fall forever. But it does the best job a parabola can do of approximating this curve near this point. Okay? So then, what about a degree 3 polynomial? Well, the x cubed wouldn't make it any better, so the x cubed term is 0. So this is still the best degree 3 or less polynomial to approximate the cosine graph. But then I've got the next term in my power series was 1 over 24 x to the 4th plus 1 over 24 x to the 24th. I'm not exactly sure what this would look like. I had to graph it to be clear, but it's going to be something like this. You probably can't see that. Let me try a different color. And not a fine marker. Let me erase the parabola. I think red's the best I've got. Okay, so probably this degree 4 polynomial, it opens upward because it's a positive leading coefficient on the x to the 4th. It's probably going to look something like this. So it follows closely this middle hill and does its best to get down into these, but then it's going to go up on at the two ends. So it's doing a better job at approximating more of the cosine graph than the degree 2 approximation. Okay, so if you keep going, as you add more and more of these terms from the Taylor series, from the Maclaurin series, your polynomial graph that you get is kind of trying to approximate more of this cosine curve. So it gets kind of, it has more and more hills and hugs closer and closer to the cosine curve for a greater length of values. So what we're saying essentially is, if we take the limit, if we take infinitely many of these terms, then the resulting graph is actually the cosine curve. Now, what that exactly means in terms of limits is takes a little bit more explanation. But this is the graphical idea of what these infinite power series are doing. If you take more and more terms, you get a better and better polynomial approximation of your curve on whatever the radius of convergence is. So since the power series for cosine had an infinite radius of convergence, if we take enough terms, this will be a really good approximation way out in both directions. Now, some of these examples, some of these Taylor series or Maclaurin series have a small radius of convergence, like a radius of convergence of, say, 1, like 1 over 1 minus x, that had a radius of 1. In that case, it'll do a good job on that radius eventually, but not beyond it. It's not going to converge to the curve beyond that radius. Okay, so I just wanted to give you a little bit of an explanation. Let me finish up this lecture with one more example of something we're doing previously. So in the previous lecture, we were talking about integrating using power series. So I'll put more instruction, but suppose I asked you to integrate the function e to the negative x squared dx. Now, it's been a while. Back in chapter 7, at the end of chapter 7, after we learned all of our different integration techniques, I was telling you about how even with all those integration techniques, there are still functions that we cannot integrate using elementary functions. This is one of them. So this function cannot be integrated. I can't get an answer which is expressed in terms of elementary functions. So up till now, we didn't really have a way of solving this integral, of doing anything meaningful with this integral. But if we use power series, so integrate as a power series, well, we just learned what the power series for e to the x is, so I can use that power series to determine the power series for e to the negative x squared. So this power series would be 1 over n factorial times the x expression, the expression that's replacing x to the nth power. So negative x squared to the nth power from n equals 0 to infinity. So again, once we change something into a power series, that's treated just like a polynomial by this integral. So it looks messy, but this integral is now easy. And all we have to do is first simplify the expression a little bit. So we separate out the x power and whatever coefficient there is. So that's negative 1 to the n divided by n factorial times x to the 2n. So we're just separating it into a coefficient and a power of x. Now we integrate this using the power rule for x powers. So this will be, I'm going to integrate first. You put the integration constant in front. So c plus the integral of, summation of, I keep the coefficient that's already there. So negative 1 to the n over n factorial. And then x to the 2n, that is just a power function. So I add 1 to the exponent, x to the 2n plus 1. And I divide by the new exponent, which is 2n plus 1. N equals 0 to infinity. So that power series, which you can check, that power series has infinite radius of convergence. That power series is an antiderivative for e to the negative x squared. But this power series does not have an elementary. This power series cannot be written as a formula using elementary functions. It can't be written as a finite closed formula using elementary functions. So power series doesn't count as an elementary function construction. Okay, but with our facts about alternating series, this is an alternating series now. If I want to plug in a specific x value, I can approximate the value that this takes by taking enough terms from this summation. Adding up the first however many terms of this summation will give me a pretty good approximation for the function value. So it is a usable formula. Excuse me. It is a usable formula. It's just not perfect. I can't get exact values. I can get very, very good approximation. I just can't get exact values. All right. So wrapping up this section and chapter, I'll put some problems at the end of this video from 11.10. We'll have an assignment and quiz over these last three sections of chapter 11. So 11.8, 9, and 10 about power series. There'll be a quiz about those. The only thing remaining, so I will do one, possibly two more videos about some basic differential equation stuff. Given the circumstances, I'm not going to go too deeply into it, but I will talk about them because technically I was supposed to do something to make up for the snow days that we had before all this happened, and my plan for that was to have a worksheet over differential equations. So we'll do that just to say we did, because it is an optional section for us in this course. All right, so let me stop this video here.